Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sababau from the Physics Section Pusat Pengajian Pendidikan Jarak Jauh Universiti Sains Malaysia. This is course JIF 318 Quantum Mechanics. In chapter 5 will be on some mathematical formalism such as linear algebra, matrices and direct notation. This is segment for Unit 5.1 on commutators. The objectives of this lesson is that after this lesson, you should be able to describe the properties of commutators and to determine whether two operators are commutative or not. The question of whether or not operators commute is of central importance in quantum mechanics. That means most of the time we need to determine whether the operators used in quantum mechanics in our operations are commutative or not. So what is commutators? For any two operators A and B, the commutator is A, B in square bracket is equal to AB. That means operators A multiplied by operator B minus BA. So these are the definition of commutators. That means A commutate B equal to AB minus BA. When two operators do commute with each other, their commutator is 0. That means if in the above example, A and B are commutative, then AB minus BA should give you a 0 value. And as an example, commutator of operator H and operator P. Actually, the P here you have a cap there, but I couldn't find a symbol for P with a cap there. Okay. H is basically a Hamiltonian operator which we had come across previously, and P is the momentum operator. Calculate the commutator of one-dimensional Hamiltonian operator H and the one-dimensional momentum operator P. So we want to check whether Hamiltonian operator and momentum operator is commutative or not. So we put the H and P in square bracket like this to show that we are trying to commute them. So HP psi equal to HP psi minus PH psi. Then we put in the actual definition for the operators. For Hamiltonian, it is negative H bar squared per 2m delta squared per delta x squared plus potential B. Then for the P, operator for the momentum is negative IH bar d per dx actually, but now we are actually differentiating psi, so we have psi here. Then minus the opposite, that means negative IH bar dx d per dx. Okay. Minus h bar squared per 2m delta squared psi per delta x squared plus b. And we run the mathematical operation. For example, in the left here, we have delta q per delta x squared when we multiply the first term of the first square bracket with the term in the second bracket. Okay, and so on and so forth. Then finally, we have this value IH bar delta B per delta X multiplied by psi. Okay. So the operator for the psi here is actually the results of the commutating process. That means HP, commutator of HP is equal to IH bar delta V per delta X, which is not equal to 0. So our conclusion with this is that H and P, that means the operator for Hamiltonian or Hamilton operator, is not commutative with the momentum operator. So it is not commutative because the commutation of H and P does not equal to 0. So general properties of commutators, that means as a whole, if you have A commuting with B equal to negative B commuting with A, if we are commuting the same operator, it is equal to 0. Then if we are commuting the summation of two operators with another operator, then basically we can split it out. AC plus BC. And if you are commuting an operator with a product of two operators, then basically we can also bring this in the form A, B, commutator A and B multiplied by C plus B, commutator of AC. What is the importance of commutators? Suppose we have a particle for which we want to measure two different observable A and B, small a and small b. A and B are eigenvalues. Okay. Is it possible for a particle to be in a state of definite A and definite B at the same time? That's the question. If you have two different observables, that means two eigenvalues A and B. The answer is yes, but only if the corresponding operators B, A and B commute. That means two observables can be measured at the same time if the operators of the two values commutative. Okay. In order for the particle to be in a state of definite A, it must be an eigenfunction of A with eigenvalue A, small a. Okay, that means we have this relationship. I think now you are quite familiar with this relationship. You have an operator A multiplied by an eigenfunction psi equal to small a, which is an eigenvalue, and multiplied by eigenfunction psi. Suppose that A and B do commute. That means they are commutative, so that the commutator of A and B equals to 0. Operating both sides with operator B. That means we multiply the above equation with operator B. So we have B, operator A psi equal to operator B, A psi. Okay. But A is an eigenvalue. We can bring this up to the front. So we have eigenvalue A, small a, operator B, Y. Okay. You have this relationship. That means now we have this relationship in the sense that two operators multiplied by psi equal to an eigenvalue and an operator multiplied by psi. But operator A commutes with B, so we can rewrite the left hand side of the equation to get like this. Okay, operator A, then inside the bracket operator B psi, and equal to A. This is as if the thing in the brackets here is the eigenfunction. So this is operator A. You have eigenvalues A, small a here. So operator B psi is an eigenfunction. That means the terms in the bracket can be considered as an eigenfunction of A with eigenvalue A, small a. We had assumed that the eigenfunctions of A of operator A were all non-degenerate, so that any eigenfunction of operator A with eigenvalue A, small a, must simply be a multiple of psi. The same goes for operator B psi. That means if uh, we have this relationship above for operator A, then for operator B it is straightforward. Operator B multiplied by psi equal to eigenvalue small b multiplied by psi, where psi is the eigenfunction. Hence, psi is simultaneously an eigenfunction of both. Since we have those two relationships, uh, initially in terms of operator A, like this, then in terms of operator B, then we can say that psi is simultaneously an eigenfunction of both operator A and operator B. That means since operator A correspond to eigenvalue A small a and operator B correspond to eigenvalue B, then we can conclude the particle is in a state of definite eigenvalue A and eigenvalue B. That means at the same time, both quantities can be measured simultaneously. This only happens if operator A and operator B are commutative. Let us check on the momentum and position operators. Consider the one-dimensional case of momentum operator and position operators. That means P and X. Then we have operator P commute with operator X multiplied by psi equal to, then we put in the definition of the operator. Momentum operator is negative I H bar delta X. Okay, that's the definition of momentum operator. Operator X, that means the position, is equivalent to the small x here, the position, multiplied by psi. This is actually on the left. The first term is operator P multiplied by operator X multiplied by psi. Then on the right hand side, actually operator X multiplied by operator P. Operator P is negative I H bar delta per delta X, but now we have psi multiplied with it, so actually this is the differential for psi. Okay, and when we solve this equation, basically when we differentiate, for example, delta X here per delta X is equal to 1, so we are left with I H bar psi minus X minus here. Okay, so we have this solution finally, negative IH bar psi. Okay, and that means the commutator of P and X equal to negative IH bar, which is not equal to 0. That means it is not commutative. That means the momentum and position operators are not commutative. A particle can never be in a state which is simultaneously a state of definite momentum, and a state of definite position. Cannot be simultaneously. So this is in accordance with the Heisenberg uncertainty principle. Remember Heisenberg uncertainty principle in modern physics, that you cannot determine the exact position of a particle and at the same time to determine the exact momentum. So that means since P and X here, we can prove that Heisenberg uncertainty principle by using the commutative properties of operators. And this provides us with a useful blueprints. For example, we usually want our system to satisfy the time-independent Schrodinger equation. The function is an eigenfunction of operator H and represents a state of definite energy E. Okay, usually in time-independent Schrödinger equation, we want to determine the eigenfunction. The wave function depends on the eigenfunction of operator H. That means Hamiltonian operator, and also represent a state of definite energy E. Then you want to find a set of operators, for example, operator A, operator B, operator C, and so on and so forth, which all commute with operator H and also with each other. So the commutation with H is given here. If we want them all to be commutative, so commutator of H and A equal to 0, H and B equal to 0, H and C, and so on. You can put so many things, commutators of operators with respect to Hamiltonian operator equal to 0. Then, of course, the commutator of the other operators apart from Hamiltonian operator H to be also commutative. That means A, B, 0, A, C, 0, B, C, 0, and so on and so forth. Okay. So this is the extension of the properties of the commutative of the commutator of operators. The fact that all these operators commute with each other means that we can find a wave function for which Hamiltonian operator psi equal to energy psi, operator A psi equal to eigenvalue small a psi, operator B psi equal to eigenvalue B psi. That means those are the forms of operators. Okay. The set of eigenvalues E, A, B can be used to specify psi, and this will give you good quantum numbers. That means commutative operators provide us with definite eigenvalues, more than one eigenvalues at the same time. As a conclusion, two different observables of a particle may be measured at the same time. Same time, that means simultaneously. If their corresponding operators commute, that means if the corresponding operators are commutative. Thank you very much for your attention.